a Portland Community College mathematics telecourse, a course in arithmetic review, produced at Portland Community College. Before we discuss how to reduce a fraction, let's look a little bit more closely about what really is entailed in different forms of fractions. Notice in this case, if the rectangle is to represent a whole, then we've divided, right here, the whole into three parts. And the shaded portion is one out of those three. See what all this symbol here means? Out of, divided by many, many others. So I have one part out of three divisions of the whole. But let's divide the whole differently. In this representation, we've divided the whole into 6 parts, and now the shaded portion occupies 2 of those 6. So we could call the same shaded portion 2 out of 6 or 2/6. But it's still the same shaded portion. So it must be that the number 2/6 and the number 1/3 are really the same number, although they certainly look different. But we could subdivide this whole innumerable different ways. Let's try one more. Now we've divided the whole into many smaller parts. 3, 6, 9, 12. Can you see that I'm counting in multiples? 3, 6, 9, 12. So now we've divided the whole into 12 parts. And the shaded portion, the same shaded portion, now occupies 1, 2, 3, 4 of those 12 subdivisions. But the same shaded portion has been used every single time. So it must be that the number 2/6, the number 4/12, and the number 1/3 are all representatives of the same number. If that's the case, then it appears that we could continue this process indefinitely and in fact have millions and millions of forms of exactly the same number. And that's exactly the case. But then how are we to tell that these are all really the same number? Let's look at this form for just a moment. Here we have the 4/12. Is it possible to divide both top and bottom by the same amount? Now you might say, yes, we can divide them both by 2. Then let's do it. 2 into 4 goes twice, and 2 into 12 goes 6. And we get a new form called 2/6. But notice, that's one of our equal numbers. Now, looking at that representation, we could ask the question again. Is it possible still to divide top and bottom by the same number? And the answer is again, yes. I could divide top and bottom again by 2. 2 goes into 2 once, 2 goes into 6 3. And that is our other equal fraction. Now we could again ask, is it possible to divide top and bottom by the same amount? And the answer now is no. That's the process that we call reducing. If we continuously divide top and bottom by the same amount, that process is called reducing. Until we finally get a form, a reduced form, where top and bottom are no longer divisible by any number. We call that, by the way, in more advanced math, being relatively prime. two numbers that are no longer divisible by the same other number. If we have divided top and bottom by the same amount until they are relatively prime, we say that this form is or has been reduced to lowest terms. Let's restate that to be formal. The process of dividing out common factors from both the numerator and denominator is called reducing. When this can no longer be done, we say that the fraction has been reduced to lowest terms. Now, as an aside, had we divided both of these, top and bottom, by 4, we could have got to the lowest reduced form in one move rather than 2. However many moves you take is irrelevant, as long as what you end with, the numerator and denominator, is no longer divisible by any common factor or divisor. Now let's reduce this rather messy problem to lowest terms. So you look at the top and bottom and ask, do you see anything that will divide both? Some of you will see 8. A few of you will see 4, but all of us will see 2. So let's divide top and bottom by 2. 2 goes into there, 1, 3, 2, into here, 2, 0, 4. Now this is a reduced form, but not to lowest terms, because we can see that 2 will still divide. So doing that, we get 6, 6 on top, 1, 0, 2 on the bottom, and we see that 2 will still divide. Doing so, we get 3, 3 on top, and 51 on the bottom. There's a temptation to quit here, except you'll note that if I add these digits, that's 6 and 3 will go into that, and 3 will go into that, so it's still reducible by 3. So 3 goes into 33, 11. 3 goes into 51 by 17, however you've done that division. These are prime numbers, so nothing will divide either of them except 1. So this form is that which we call reduced to lowest terms. Now this is an awful convenient form we'll use very frequently in the future, and you probably have already. It could be that 5 people can work a problem and get 5 different forms, and to a casual observer they all look different, but in fact they're all the same. So it would be awful convenient if we could agree to all write the same form. That way we just look and see if we agree to exactly the same 2 parts, top and bottom. And historically, that's exactly what has been done, is that this form will be standard from now on. In all future math problems, if your results are fractional, you will be expected to reduce it to lowest terms unless stated otherwise, and this will facilitate communications a great deal. Now let's repeat that problem and try it from a different angle. Let's try this. First, let's utilize some of the knowledge from Chapter 2 and prime factor this numerator. If you did so, and I won't show it here to gain time, but if you did so, you would get that prime factored form, not written in exponent form this time. Now let's also prime factor the denominator. And if we did that, we would get this form. And there's a rule in mathematics that says if you have a fraction in factored form, you may divide anything you want into any top factor, providing you divide the same amount into a bottom factor. So I can divide this one by 2 and this one by 2, this one and this one, this one and this one, and this one by 3 and this one by 3, until finally all I have left is that times these 1s, which of course gives me just 11/17, and it's reduced. This process of dividing into factors, top and bottom, in math is referred to as canceling. It's important to note, if you go through this process of canceling, that you can only cancel when tops and bottoms are in factored form. Let's make a formal note of that. One may cancel, that is divide, only if the numerators and denominators are in factored form. That is multipliers. And I may divide into any top and bottom factor I wish by the same amount. Sometimes that gives us a surefire way of knowing that a fraction has been reduced to lowest term. Let's pick one example. Let's reduce this fraction to lowest term not by dividing top and bottom, but by prime factoring top and bottom first. So if I were to prime factor the top, that is 2 times 2 times 3 times 7. Now we could verify this by simply multiplying this and finding that it comes out to be this. But at this point, to gain speed, we're presuming that you recall our Chapter 2 lessons and that you can do this. So on the side, if we were to prime factor 462, we would get this expression. Now we can look at these smaller numbers to catch the divisors much easier than we can the larger. We can see that 2 goes into both of those. 3 goes into both of those. 7 goes into both of those. Until finally all I have is 1 times 2 times 1 times 1, and 11 times a series of 1s. So that reduces very quickly to 2 11s. Sometimes after we reduced halfway, we don't know whether it's reduced all the way. But by prime factoring first and canceling like factors, which is really a division, we know that we have reduced to lowest term. This prime factoring is a very useful device. So first, always prime factor, then do what many books call canceling. Now, let me show you a shortcut that helps with some problems. A shortcut I think many of you might find very helpful. It stems from this particular fact about numbers. The only numbers, primes in particular, which will divide into each of 2 given numbers will also divide into their difference. An example, consider these 2 numbers. And let's say we're curious about what number will divide into both of them. Note, they're fairly close to each other in size, so it's easy to determine their difference. And in this case, it makes no difference which you subtract from which. And the difference, of course, is 21. Now, this claim is this. The only numbers that will divide these 2 must also divide this smaller number. But this number, the difference, is so small that I can see that the only prime numbers that will divide this is 2 and 7. Hence, the only candidates to divide these 2 is also 2 or 7. Well, we can see that 2 divides this, but not this, so 2 will not divide this. But if we were trying to check out the 7, see 7 goes into the 8, 7 goes into 42 6 times, so 7 does go into this number 86 times. Now let's see if it also goes into this. And by golly, it does. So 7 divides into both of these, and it also divides this. Now, had it turned out that 7 would not divide into these either, then that means there is no number that will divide each of these. It happens very frequently that you will have a fraction where the top, size-wise, is close to the bottom, size-wise. So if you were to take the difference will be a small number. Hence, it's easier to find the prime divisors of this than these two. So you take the difference, find the prime divisors of that difference, then try those prime numbers into these two, and if they will divide, do so if you're trying to reduce, and if they won't divide, you know that the given fraction is already reduced. Let's reduce a fraction by that technique. Say our chore is to reduce this rather messy fraction, if possible. Note, it's not at all obvious to see if anything will divide each of them. For all we know, it might already be in reduced form. For sure, we see that 2 will divide this, but not this. So our technique suggests that we take the difference, the smaller from the larger, and then find the prime divisors of this, which is certainly easier than this or this. So if we look at the 115, we can easily see that 5 goes into this immediately. So doing so, we get this, and we see this is a prime number. So this only has the prime factors 5 and 23. So our shortcut technique says the only candidates to reduce this is either 5 or 23. Well, we can see by our divisibility test, by looking at these n digits, that 5 won't. So that means this is reducible by 23, or it's already reduced. So what we want to do now is to try to reduce, or divide, 21 into 644, 23 rather. And we won't worry about the bottom until we see if this will go in here, because if it won't, then who cares if it goes into the bottom? It's reduced. Okay, so trying to divide this into this, we get 28. I didn't show the work here. So 23 will divide into here. Now if it divides in here, then the fraction is reducible by 23. So we'll try 23 into this one, and if we do, it comes out 33. I've already done the work to save us time. You might want to check it. And of course, checking's easy. We simply multiply these two, see if it does come out to be this. So 23 goes into the top 28 times, and 23 goes into the bottom, or denominator, 33 times. And the only candidates to reduce this were the same two numbers I had here. And we can see that 23 will not go into either of these. So our given fraction has been reduced. And you see by taking their difference, because they were fairly close together, gave us prime factors and gave us a small list of numbers to try our division by, rather than trying all the numbers. That can save us a lot of time if you remember this, and in particular if the denominator and numerator are close to each other in size, so their difference is relatively small. It's a nice trick, isn't it? Let's try another one. This is even a better candidate for this technique because the two are even closer to each other. 485 subtracted from 491, we can see, is 6. And the only prime divisors of 6 is 2 and 3. But we can rule out 2 immediately because neither of these are even. 3 we can try by our divisibility test. 4 and 8 is 12, and 5 is 17. 3 won't go into here, so we won't even bother trying this. So this tells me our fraction's already reduced. See, this is much, much faster than trying all the possible numbers that will divide these two to see if they will work. This gives us only 2 numbers to try. And if neither one of them will divide, which happens in this case, the fraction is already in reduced form. So you see that essentially you've been given 3 techniques for reducing fractions in this lesson. So one might ask, well, which of those 3 techniques do I use? Logically, it makes no difference. Any one will work. But let's look at each of them once again, and perhaps we can see when one might work better than the other. The first and most common technique simply suggests that you observe the 2 numbers, search your memory, and divide out any common divisors. So these are small enough that we know that 2 will divide both of them. Someone else might say, yes, but 3 also divides both of them. So that would be a good trial too. Someone else might say, no, 6 will also work, so that's even better. So 6 divides into 18 3 times, 6 goes into 24 4 times, and we're done. So this technique, which is the one that most people are familiar with, works the best when the fractions are small and common divisors are fairly obvious. The second technique suggested by your textbook suggests that we prime factor the numerator and denominator. And if we did in this case, the 84 would prime factor into 2 times 2 times 3 times 7. I won't show you the work here. Again, we're presuming that you're quite good at this from previous lessons and the previous chapter. And in like manner, if you prime factor the bottom, you would get 2 times 2 times 3 times 3 times 3. Then having prime factored top and bottom, all you need to do is to cancel the like factors. And when there's nothing remains factor-wise to cancel out, you multiply back the remaining factors, top and bottom, and what you have is in reduced form. One might suggest here that it would seem more obvious that since you can obviously see that 2 will go into top and bottom, why don't you do it by 2 first until you can't see anymore, then prime factor. And that's a good suggestion. That usually is the best way. This technique is a technique that will work best for those of you who will be going on to algebra. For algebraic expressions, this factoring technique is usually the only way an algebraic fraction can be reduced. And our third technique, which was not given to you in the textbook, is that we take the difference between the numerator and denominator, which in this case is 30 rather, and prime factor only this difference. So we can see that 2 goes into there 15 times, 3 goes into the 15 5 times. So the only prime divisors of the difference of these 2 is 2, 3, and 5. So this tells me the only candidates I should try to reduce these is the 2, the 3, and the 5. Well, we can see since these aren't even that 2 won't work. Since it doesn't end in 0 or 5, the 5 won't work. So that leaves only the 3. And using the divisibility test, 5 and 7 is divisible by 3, that's 12. So therefore 507 is. So we divide 3 into 507, we would get 169. And using the 3's divisibility test on the denominator, 5 and 3 is 8 and 7 is 15, which is divisible by 3, then this 2 is divisible by 3. So dividing 537 by 3, we would get 179. Now 3 still might work again. It is not necessary that it only works once. So if we use the divisibility test on the top, 1 and 9 is 10 and 6 is 16. 3 won't go into this, so we don't care if it'll go into this. so our fraction is in reduced form. This technique obviously works the best when these two are fairly close together. Technically, all three techniques work at any time. So it's simply a matter of which one do you prefer and which one at any one moment seems to be the easiest. And that seems to be more of a personal choice than a matter of real tight logic. Now, let's continue in these last few minutes our ongoing review over prime factoring and least common multiple. I hope you're beginning to draw the conclusion over these last few lessons that this must be very important if this person takes the trouble to review it over and over at the end of each and every one of these lessons in fractions. And the answer to that is yes, it's going to be extremely important. Within a few lessons, this type of problem you must be able to do routinely and quickly, just like this. So if you can't at this moment, this review is especially for you. And if you can, then watch this and see if you can teach yourself to even speed up the process. So you will recall from chapter 2 that if we wish to find the least common multiple of two numbers, what we're really asking for is what is the smallest number that each of 28 and 35 will divide into. For sure it's going to have to be 35 or larger, because 35 is the smallest that 35 will divide into. So since we only have about 1 or 2 minutes left, let's just summarize quickly the techniques that you were given towards the end of chapter 2. To find the least common multiples of a series of numbers, in our case just 2, the first thing we were asked to do was to prime factor each number and write in exponent form. So we are asked to prime factor 28 and write it in exponent form. So rather than take our time here, I'll presume that you can do this now. If not, you must go back and do yet once again a review over that. So doing this, we would get 2 squared times 7. See, 2 times 2 is 4, times 7 is 28. And you can probably just see that 35 is 5 times 7. So we have prime factored each of these and written it in exponent form. Then we were asked to list each different base of those prime factorizations. In this case, a 2, a 7, and a 5. And finally, give to each of those bases its highest exponent used in the initial prime factorizations. So 2 has the highest exponent of 2, 5 is 1, and 7 is also 1. Then this number, whatever it is when you multiply it out, is the least common multiple of these two numbers. And this is easy enough to multiply. This 2 times 2 is 4, times 5 is 20, times 7 is 140. So our claim is that 140 is the smallest number that each of these will divide into. Now, bring recall or memory of that process with you into the next 2 lessons, and we'll review a bit deeper. This is your host, Bob Fennell.